Linear regression. This is one of the most important tools that you will use in business analytics. Linear regression basically involves you drawing a relationship between two independent things. And the reason you want to do that is so that you can build a model that will help you project what future values will be. So let's talk about this process and how it works. Managerial decisions are often based on the relationship between two variables or more variables. Here's an example for you. Let's say you're in New York and you own a pizza parlor, and there's a subway station not far from your pizza parlor. When you wonder if there's a relationship between the people getting off the subway station at that stop and the amount of pizza you're able to sell. Why would that be important? Maybe you have to do some more marketing, or maybe you have to do something to get your pizza in front of these wonderful customers of the subway and people that travel using public transportation. The relationship between the travelers, the number of people that stop at that particular intersection, and your pizza place could be something you could use to sell more pizza. So linear regression is something you could use to figure that out. In order to do linear regression, there are three things that you need to know. First, you need to know what your dependent variable is. That is the variable that's being predicted. You also need to know what your independent variable is. That is the one that is used to predict the value of the dependent variable. Once you have those two in mind, then you can do a simple regression, which is an analysis involving one independent variable and one dependent variable. One way to look at it is thinking about making a cake. A cake has many ingredients in it, but the sweetness of the cake is determined by the amount of sugar that you put into it. So the independent variable would be the cups of sugar, and the dependent variable in this analysis would be how sweet the actual cake turns out to be. The more sugar you put in, the sweeter the cake. So there is an analysis between the two to know that the more sugar that I put into the cake, I know it's going to be sweeter. That in and of itself is a simple way to look at regression. And in this case, a simple regression with two things that you're looking at. The regression analysis for which one unit change in the independent variable is assumed to result in a same change for the dependent variable. That is what we call linear regression. Just like back in school when we learned algebra for the first time, the x would be the independent variable. It has a function, and then that function, once you put the x in, gives you a y. So the y becomes the dependent variable because it's dependent on the x. Simple regression only deals with two variables, x and y, where multiple regression deals with multiple independent variables. For example, if I go back to the cake example, we talked about how much sugar I put in would make the cake sweet, so that could be single regression. However, the cake also has in it cinnamon. It also has in it eggs. It also has in it milk. So if we were able to determine how good the cake is based off of the sugar you put in the cake, the milk you put in the cake, the cinnamon you put in the cake, and for some of those out there, the chocolate that you put in the cake and on the cake as part of the frosting, all of those independent variables come together to help you determine how good the cake is. That is a way that you could look at multiple regression, which is where you have multiple independent variables that can be used to determine the value of the dependent variable. So let's talk about the regression model. The model basically is this. The formula on the slide says that y, which is the dependent variable, is equal to beta sub 0 plus beta sub 1 times x, which is the independent variable, plus e. E in this case represents error. The beta sub 0 is what we call the intercept. The intercept is what would be predicted for the value of the relationship if the independent variable is equal to 0. So the beta 1 would be the slope of the formula or model that you would put together. You multiply that times the independent variable of x. And then, of course, the E, which is the error, represents how much error there is between what you're predicting versus what the actual value is. So if we look at the regression equation, the equation describes how the expected value of y, denoted E of y, is related to x. So the expected value in a regression equation is simply the intercept, beta sub 0, plus beta sub 1, which is the slope, times the independent variable of x. At the end of the day, when we put together a regression equation, we are building a model that's going to help us predict future values according to the patterns that we see based on the relationship between the independent variable and the dependent variable. If you look at figure 4.1, you'll see panel A, panel B, panel C, and you will see 3 different types of relationships that can be graphed. The first one is a positive linear regression, or a linear relationship. So you see the intercept B sub 1, or beta sub 1, and you see the upward slope of the line. That means that the slope is positive. If you look at panel B, the negative linear relationship, you see that you have beta sub 0, the intercept, but then you see a line sloping down and to the right. That means that the slope of this particular line and this relationship is negative. Then you can also have no relationship, which is panel C. The parameter values are usually not known and must be estimated using sample data. So sample statistics, noted by B sub 0 and B sub 1, are computed as estimates of the population parameters, beta sub 0 and beta sub 1. So the key thing to notice with this is when we're dealing with a sample, a smaller subset of the overall population, we're trying to estimate what the relationship is going to be of the larger population. The equation obtained by substituting the values of the sample statistics B sub 0 and B sub 1 for beta sub 0 and beta sub 1 in the regression equation. That is the estimated regression equation that we want to go after. Here's an example of a simple linear regression equation using the sample statistics. So the y hat is equal to B sub O plus B sub 1 times x, where the y hat is equal to the point estimator for the expected value of the relationship between x and y. B sub 0 is the estimated y-intercept, and B sub 1 is the estimated slope. And the reason it's estimated is because we're using sample data in order to figure this out versus using all the data of a population in order to calculate the relationship. Now, when you're doing a regression analysis, one of the things that you want to be aware of is this process called the least squares method. We use the least squares method to help determine what the estimates are for the intercept and the slope. And here's the interpretation of them. The slope, B sub 1, is the estimated change in the mean of the dependent variable y that is associated with a 1 unit increase in the independent variable x. The y-intercept, B sub 0, is the estimated value of the dependent variable y when the independent variable x is equal to 0. In order to let this come alive a little bit, let's take an example. So if you look at table 4.1, this is a table of data related to a trucking company. So what we have is the driving assignments, which is represented by the variable I, and the number of miles traveled, represented by the variable x, and the travel time, which is represented by the variable y. So what we want to do is build a simple regression analysis to understand the relationship between miles traveled and the time traveled. Figure 4.3 is a scatter chart of the data that we just took a look at. So if you were able to plot the data, you can see that there's starting to be a relationship between miles traveled, which is going to be our independent variable, and the travel time, which is going to be the dependent variable. By looking at this chart, you see the data basically sloping up and to the right, which gives me the idea that this is going to be a positive relationship. So let's see if that is what it is. The least squares method follows this format. You minimize, which is what the MIN means, the summation of the observed value, which is y sub I, minus the predicted value, y hat sub I, squared. Now, when you square that difference, that is going to be the thing that you look at to determine if you have a good fitting regression analysis and a good fitting line. The ith residual. That is the error made using the regression model to estimate the mean value of the dependent variable for the ith observation. It is denoted by E sub I equals Y sub I minus Y hat sub I. That would be the error that you want to reduce when you're doing a regression analysis to make sure that your model fits the data as tightly as possible. Our job is finding the regression that minimizes the sum of the squared errors. In order to use the least squares method with the data that we just presented, we have to build out the slope equation and the intercept equation. The slope equation is b sub 1 is equal to the summation of each x parameter minus the mean of all the x parameters times each y parameter minus the mean of each y that you have divided by the summation of each x parameter minus the mean of x squared. That's a lot to take in, but at the end of the day, you're basically trying to figure out the slope between all of the different pieces of data that you have, all the observations, and this is the formula that helps you do that. The intercept equation is simply the b sub 0 equal to the y mean, or the mean of y, we should say, minus the b1 that you just figured out, b sub 1, times the mean of x, which is the value of the independent variable for the ith observation. Now, if you're able to plug in all of your numbers, you'll be able to come up with both of those parameters. So let's do that. For the Butler Trucking Company, using table 4.1's data, the estimated slope of b sub 1 is equal to 0.0678. The y-intercept, once we have that slope of b sub 0, is equal to 1.2739. Based on those two pieces of data, we now can create a simple linear regression model, and it would look like this. Y hat, or the predicted y for this relationship, is equal to 1.2739, which is the intercept, plus 0.0678 x sub 1, which would be the value of your independent variable. Here's the interpretation of the regression model. If the length of a driving assignment were 1 unit or 1 mile longer, the mean travel time for that driving assignment would be 0.0678 units, or 0.0678 hours, which is approximately 4 minutes longer. Here's the interpretation for the b sub 0. If the driving distance for the driving assignment was 0 units, then the mean travel time would be 1.2739 units. Using the estimated model and the known values for the miles, we can estimate mean travel time in hours. For example, the first driving assignment in the table, table 4.1, has a value of miles traveled of x equals 100. The mean travel time in hours for this driving assignment is estimated to be y hat sub 1, which is equal to 1.2739, which is the intercept, plus 0.0678 times 100, which is the miles traveled. That equals 8.0539. The resulting residual of that estimate now is equal to 9.3 minus 8.0539, which is 1.2461. And you may be saying, well, what does that really mean? Well, let's look at table 4.2 to get an answer to that question. In looking at the data in table 4.2, we can take each of the driving assignments. We could take each of the miles recorded for the driving assignment, which is represented by the X variable. We can take the travel time in hours, represented by the Y variable, and now figure out what the travel time should be based on our model. When we do that, we end up with a number that we can now figure out how close that number is to the actual data we have. That is represented by E sub I. As you look at this chart, you see all of the values of E sub I, which is equal to the observed value minus the predicted value using our model. E squared sub I is the least squared method. So as you look through the data, you'll see, for example, for the first driving assignment, 1.5. That's how much error is in the estimate. If you look at driving assignment 5, you'll see 0.2164. That's how much error is in the estimate versus the actual data that we have at that point. So if you add them all up, you'll see that the total of error, or the least sum squared method, when we use that, the total for all of the error there is equal to 8.0288. Now that we have a model, it's very easy to graphically show you what that model looks like. So on figure 4.4, you see the data that we had represented by the blue dots, and then you see a straight line, which is represented by the simple regression equation that we were able to put together based on the sample data. At first glance, the straight line, as it's plotted on the same scatter chart as the data that's there, pretty much is close to a lot of the dots that we already have. That's representative of what our estimate would be using the sample data. This is a good sign because using your visualization of the data, you can see that your model is pretty close. It's not accurate, or it's not completely right for every data point. However, it is close as far as the pattern that you're seeing as you go and increase the number of miles traveled versus the travel time in the dependent variable. That was an introduction to linear regression. This process is going to be used throughout your business analytics problems and your career if you decide to go into this field. You're going to figure out the relationship between different things, different variables. And by understanding the relationship and building a model using that understanding, you can now take that and predict future values, which will help you as you try to figure out patterns and trends in the data you're analyzing.